Okay, this is David Zierler, Director of the Caltech Heritage Project. I'm delighted to be back with Professor David J. Stevenson. Dave, it's great to see you again.
Good to see you.
Dave, I'd like to return to an earlier comment you made that I think would be important to get some clarification on, and that is prior to coming to Cornell, you really did not have any exposure or were aware of the field of planetary science. And so, did you study what you would later come to appreciate that would be called planetary science at all as an undergraduate? Or not just the nomenclature, but the entire field, the discipline, was new to you when you arrived in Ithaca?
The entire field was new to me. I knew a little bit about astronomy. I had a little bit of curiosity about Jupiter, although that came from Neil Ashcroft when I was already doing my master's degree. But essentially, I went to Cornell unaware of planetary science as a legitimate scientific discipline.
So what was the game plan? What were your intentions prior to arriving at Cornell?
They were vague. I had this vague notion that it would be fun to do something that involved condensed matter physics. I had this vague notion that astrophysics was of interest to me. I knew of one person, that's Ed Saltpeter, who did these kinds of things. He wasn't the reason I went to Cornell, but I was certainly aware that that was a possibility.
You left off the list particle physics, which is interesting because this was a particularly exciting time for the field.
I did not know much about particle physics either. I did not think of that as a direction to take. And I think that in part is ignorance. You know, that's not so unusual. I think it's quite common for people at the time of entering graduate school, quite common for people to have rather little understanding of the field as a whole. I even think that people sometimes make choices too early. And by the way, that's part of why I wanted to go to the United States, because it seemed as though the options were greater. If you went into the English system, which for me would have meant Cambridge, then you had to choose right at the outset. I did not feel comfortable with that.
So it was a good place in terms of going there and really exploring, following your interests, seeing what was compelling to you.
Yes.
On the cultural side, just arriving in the United States, what were your initial impressions?
So I knew very little about the United States. I came from a country that was influenced by both the United Kingdom and the United States through, for example, comic books and so forth. So I had seen Superman comic books and Batman and so forth. My parents didn't like Batman. And some of the popular culture through radio, no television. A little bit of television just before I left. So I had some awareness of US culture, but not a great deal. I do remember what you might call culture shock of arriving actually in Honolulu, because in those days, of course, you could not go directly from New Zealand, nonstop from New Zealand to, for example, Los Angeles or San Francisco. That was impossible. So you had to go through Honolulu. And I remember sitting in the airport and there were people sitting in chairs watching television and so forth, for which they had to pay. And all of that was new to me. But upstate New York was not hugely different. I mean, obviously the culture is different, but what I saw at Cornell fitted fairly comfortably with my background. It wasn't as big a shock as I think it would be for somebody coming from Asia, say.
Between your wardrobe and your constitution, how well prepared were you for that first New York winter?
Well, I actually had to buy a really good winter coat. I remember that after I arrived at Cornell. Of course, I arrived there in late summer. It was beautifully sunny. Cornell is actually quite nice in the fall. It can be miserable most of the rest of the year. It snowed on Thanksgiving. Thanksgiving was a novelty to me. I actually went to Neil Ashcroft's house, and there was snow on the ground. And so, yes, I had to get used to that. And I learned to ski in Ithaca, which was not easy because Ithaca is not a good place for skiing. Ithaca does not have a particularly good climate. And the problem is that it oscillates in temperature so that you get snow, the snow partially melts, it becomes ice, it gets mixed in with the mud. It's actually better further north.
Yeah.
But you get used to it. When I went back to Cornell to do a sabbatical years later, I realized that it actually wasn't too bad. There was quite a bit of sunshine, even in the winter. But it is true that you get the conditions I described where it's actually not quite cold enough that you have the right kind of conditions. Of course, upstate New York, especially when you get up to Syracuse and to Buffalo, has a very large amount of snow. And that's called the lake effect. It's because of Lake Ontario. It's not quite so evident in Ithaca. Ithaca, by the way, is still a nice place, but it was even nicer back then. It's a pleasant environment, the lake, the gorges, the area around Cornell. It's really different from Harvard or MIT or even Princeton. It's not rural, it's actually a pocket of progressive points of view, whereas a lot of upstate New York in the political language would be regarded as Republican. But it is a nice place.
Dave, what about politically, coming in as the Vietnam War was grinding on and all of the political tumult from the Nixon administration? How did you deal with those issues on campus?
Well, the environment at Cornell is certainly to the left of the general environment in the United States. I think that is still true. They had problems, many of which predated the time I was there. There was a famous incident that happened before I arrived, which showed up on the front page of the New York Times, where there were African-American students with guns in front of the main student building called Willard Straight, a building I got to know well, but I never saw that aspect. But of course, I did see demonstrations. The demonstrations were supported by some of the faculty. I was apolitical, but I was certainly aware of those events and aware of the generally progressive view, which was against the Vietnam War and the things that followed on from that. I even had to leave the room in the dormitory where I lived because of tear gas or pepper gas that was released in the streets immediately below at the time of the protests to the Cambodian bombing. I also remember the generally positive attitude, this is years later, but the generally positive attitude when Nixon resigned.
When you got to the department and you were open-minded, what was your sense of the things that were most exciting? What was going on with the faculty and other graduate students that might have provided some direction for you in those early days?
Well, I certainly was attracted to the kind of science that Ed Saltpeter did, which was the application of many aspects of physics, but in particular condensed matter physics, to bodies. He had already worked on white dwarfs. And so I was attracted to condensed matter physics, which was then called solid state physics, but also to astrophysics. Those were the things that I noticed most. I was aware that Cornell had a synchrotron. I was aware that there were people starting on the work that eventually led to a Nobel Prize having to do with superfluid helium-3, David Merman was involved. Doug Osheroff, who was a student, slightly older than me, was involved. Bob Lee, the professors associated with that were involved, Dave Lee and Bob Richardson. So I was aware that there was a wide variety of things. But even though I was a little bit vague about what interested me most, and I wanted to pick that up in classes, I must admit that it was the attraction of condensed matter physics, which Cornell was very strong in, and had people doing lab experiments, but also people doing theory. And that was one of the strengths, that it had that balance. It had a balance between experimental and theoretical work. Ed Saltpeter, of course, was in the building that was nominally nuclear physics, just along the corridor from Hans Bethe. And so you had the condensed matter physics in one building, and then another building next door that was doing nuclear physics, which was merging with elementary particle physics. And then you had a separate building again, which was also strong, which was the place where they ran Arecibo and one of the centers of planetary science. I wasn't aware, as I said, of planetary science at that time. When I chased down Ed Saltpeter after arriving at Cornell, he correctly told me to do an elementary class rather than one of the ones he was teaching. And so I took a class for Martin Howard, which was basically astronomy. And that was fine, since I'd never taken anything like that before. But I was at that point mixing things that would have been labeled astronomy with things that were basic physics. The Cornell curriculum, by the way, unlike some schools, is quite flexible. So you have a lot of flexibility in choosing what you want to do. And that worked for me.
Hierarchically, was Hans Bethe really at the top of the pyramid in the department at that point?
I didn't see it that way. Actually, this was even before he got the Nobel Prize, although the prize was awarded for things that he had done earlier, of course, which is common. It did not seem as though there was really that much of a hierarchy. And I think that's actually good. So there were young faculty, there were older faculty. I did take a class from Hans Bethe. I was teaching assistant for a while. He was on my exam committee, the committee that decides whether you go on to do thesis work. He asked me a question in that exam, which I answered fairly well, which I think was actually important. Ed Saltpeter was there. This was even before I was really working with Ed. So Hans certainly had an influence. Hans was highly regarded, and a lot of people wanted to do well in his class. It's the only class I took where you had the sense that there was competitiveness, because you had the sense that people really wanted to do well in that class because Hans Bethe was teaching it, and it was what was called intermediate quantum mechanics, and it was well taught. And so it was in a large room. There were a lot of students. There were dogs wandering in and out. That's one of the Cornell traditions, that there are dogs wandering around. And so I remember a couple of famous occasions where Hans is lecturing and a dog comes in and sits on the floor and listens to Hans. So certainly people were aware of his presence and his importance to the physics program, but it wasn't really a hierarchy.
Dave, of course, you wouldn't have anything to compare it to in real time, but in retrospect, the intellectual atmosphere where you have people with interest that brush up against astronomy and solid-state physics, does this strike you as a uniquely interdisciplinary or multidisciplinary approach to the field?
Certainly in what Ed Saltpeter was doing. And yes, it's true that the disciplinary boundaries were not strong, and I think that's one of the good things about Cornell. I simply don't know whether that would have been true elsewhere. I doubt that it would have been true at MIT, which might have been another possible place to go. I don't know enough about how things were done at Harvard to make a comparison. Ed Saltpeter had an office in the nuclear physics building, but he had people all over the place who worked with him. He was regarded as a good advisor. And famously, we never saw each other except at parties. By that, I mean the students never saw each other. So Ed would make a phone call to one of us and say, why don't you come over and talk? And I would go and talk in his office, which was an interesting experience. But you never saw the other students except at a party. But they were there, and some of them were very distinguished. For example, Bruce Drain, who worked on interstellar matter, became very distinguished, became a professor at Princeton. I only met him by chance after we had both been working with Ed for a couple of years. And that was not unusual.
What was Ed like as a person? Was he approachable? Could you have regular conversations with him?
Ed was approachable, and you had conversations at a rate that he pretty much determined. It was a very stimulating experience because you would go into his office, which was not particularly big, and he would be standing, you would be standing, and he would say something that was startling and that you did not immediately understand. There might be something on the blackboard that was argued over, but it was the kind of situation where you might have to go away afterwards and think about it for a while to really understand what happened. Ed was not a good lecturer. It was stream of consciousness. He would arrive at a lecture seemingly a little bit flustered, moving fast, maybe with one piece of paper that only he understood, and things would show up on the blackboard in an order that he might change in real time, and almost no equal signs. Everything was approximations, which is good, but made it harder to figure out what was actually going on. So he had the reputation of not being a particularly good lecturer, but an outstanding mentor, because the conversations that you had with him were so stimulating. He was certainly friendly, and as I mentioned, he ran parties. So he would set up a party at his own home, which was within walking distance, and those were lively occasions.
Dave, do you have a specific memory of coming to the realization that planetary science was a discipline and that this is where you'd focus your efforts?
That never really happened. I was always in the physics department. I always had an office in Clark Hall, which is the place where the condensed matter physics is done. That's still true. And Ed was in nuclear physics. And Ed Saltpeter actually had a second office in what was called the Space Physics Building, but he never used it. And I never went there except to collect my paycheck or to go to seminars. And he went there to go to seminars, but that was the way things worked.
Was there an official planetary science program at Cornell?
So Cornell has a structure that is different from many places, and it's still there, and it sort of works. And the structure is one in which planetary science is within astronomy. This is not true at Caltech. It's not true at MIT. It's not true at Harvard. It's an interesting and different structure which leads to a different kind of interaction. And it seems to work at Cornell. I think that what we have here at Caltech and what is very often found elsewhere also works. I'm not sure which is best. What we have, of course, is planetary science together with the people who do earth science. Cornell, at the time I went there, was not strong in earth science. It has become stronger. It has a separate building, which is way across campus, called Snee Hall, which is where the geophysicists and so forth reside. It's an unusual history because Cornell is famous for doing everything. That's one of the selling points of Cornell, that they do everything, even figure out how to grow apples. Not far away from the astronomers because they have a state university aspect as well as being a private college. But they were not that strong in geology. They have become stronger.
What was the process intellectually, even administratively, in developing your thesis research?
It's hard to reconstruct exactly how it came about, except that I liked what Ed was doing, and I gravitated towards him, but it took time. The qualifying exam, which I mentioned, was an important part of alerting him to the fact that I could do that kind of science. I don't think he was convinced earlier. It's perfectly understandable if you're someone who is viewed as an attractive advisor, that you have to fend people off. And I think he may have done that to some extent at an earlier stage. So certainly to begin with, since I was in the physics department, he was too, but he did other things. It was more likely for me to be doing something that was conventional condensed matter physics, and I did in fact do something with Neil Ashcroft before I worked with Ed Salpeter.
What was that? What was your project with Neil?
The project with Neil was to understand the electrical conductivity of liquid metals that arise through complete ionization. And the most obvious case is metallic hydrogen. So we actually constructed a theory which was very much consistent with the work that Neil had done previously based on work originally done by Simon in Great Britain, where you treat the liquid structure as similar to that of an ensemble of billiard balls, hard spheres. And that gives you a particular structure factor, as it's called, which is just a description in Fourier space of the distribution of the protons in the case of metallic hydrogen. And then you have a theory for the interaction between the electrons and the protons, and that can lead through a theory originally developed by Simon for the electrical conductivity. We came up with a fairly high value. It's not clear whether that's right. We also came up with ideas for the pressure above which hydrogen becomes a quantum fluid, meaning that it melts at absolute zero because of zero-point motion. So this work was motivated, I suppose you could say, a little bit by Jupiter, but I wasn't really thinking about Jupiter that much at the time.
When Ken Wilson was developing his ideas on renormalization, was there a general sense in real time just how revolutionary this thinking was, or did that process happen more gradually?
I'm not sure how we realized it, but it's clear that we knew something revolutionary was happening. It might have come from somebody like Michael Fisher, who was in the chemistry department. Another example of the strength of Cornell, that you had people like Fisher, who was basically operating like a physicist, but in the chemistry department. That's still true with people like Hoffman. It's something special and very good about Cornell. So somehow we as students, I can remember this even in the first year, we became aware that something special was happening. And I can even remember Ken Wilson was also in the nuclear physics building where Salpeter was and Hans Peter was. I can even remember going over to that building with another student, perhaps at the end of the first year, to get a copy of stuff that had not been published yet, that Ken Wilson had written. I don't think we talked to Ken directly. We must have talked to a secretary or someone, but anyway, we got a hold of the notes because we knew that something special was happening. Of course, the story is that Ken Wilson, who had worked with Murray Gell-Mann, wanted first to understand elementary particle physics, but then realized there was an easier problem, which is the Kondo effect, which is in condensed matter physics. And so the renormalization group ideas moved over to an application to critical point phenomena where Michael Fisher was an expert. So it was very much a Cornell story. And I can remember well when the seminar course was set up and you went into the lecture hall where Ken Wilson was to introduce the subject, and sitting directly behind me was Neil Ashcroft and John Wilkins and so forth. So you knew something special was happening because it wasn't normal for other professors to show up at a class.
What was Ed's style as a mentor? In other words, for your thesis research, did he give you a problem to work on that was related to his research agenda, or he let you go off on your own and present him with possible ideas?
He certainly gave me the idea of looking at the question of how hydrogen and helium mix, but he didn't really tell me how to do it. I had to figure that out for myself. Ed had worked on the possibility that helium settling in the giant planets was an important energy source. And he wrote a paper. I can remember at that time, I was not working with Ed, but I can remember seeing him complete that paper. In those days, you had to physically go to the library to check on references because, of course, no computer source of information of that kind. And I can remember seeing him in the library. And he was actually responding to a very famous scientist who wrote on that subject even earlier by the name of Rose Smolakowski, who I met later. He was a professor at Princeton, but of course also came from Europe and was Jewish. So Ed was responding to Smolakowski and wrote a paper in Astrophysical Journal. And he knew that a key question was unanswered, and that is whether helium would be insoluble in hydrogen when hydrogen was a metallic liquid. And so that was essentially what he was suggesting to me. He did suggest an interesting piece of information that he knew about, which turned out to be less important, and that was that Freeman Dyson, who of course he knew at the Institute for Advanced Studies, another Cornell connection actually, Freeman Dyson had worked on the lattice energy of a set of protons and alpha particles, the fully ionized state. And Freeman had shown that you actually had a lower energy state if you made an alloy. That turns out not to be relevant because if you fix the pressure, as you must, to minimize the Gibbs free energy, the electron density changes as you change composition, and that's key to understanding how the total energy changes. This was subtle, but that was my PhD thesis work, and it was a lot of work, and quite a bit of it I had to figure out for myself, although I know that some of these ideas about how to construct phase diagrams were things that Ed knew. It's not as if it was something completely new, because I can remember him once giving a seminar about hydrogen and the possibility of it being metastable. And he talked about Gibbs energy, and I had not heard about it previously. In physics, you don't, for the most part, learn about what Gibbs did. Gibbs, in my opinion, was the greatest American-born scientist of all time. There's no close competitor.
Wow!
And
Can you tell me why, Dave? That's high praise. What makes him the number one?
So Gibbs set down the framework for everything that we do in chemistry to decide on phases and composition. So when you decide where elements go in some mixture, it's Gibbs energy minimization. If you want to know what the Earth's core is made of, it's partitioning between liquid iron and the silicate that makes up the rocks, which we call the mantle. That's Gibbs energy. That's all about Gibbs energy. People don't, on all occasions, mention Gibbs, but he did it at Yale around about the time of the American Civil War. And of course, he has a postage stamp. But a lot of people in the general public have never heard of Gibbs. But he was, and of course, he did some mathematical things as well, Gibbs phenomenon and so forth. But the truly extraordinary thing, which he wrote out in an obscure way in the Transactions at the Connecticut Academy, of all places. I have a copy of it somewhere. It talks about how you decide about chemical potential. The idea of a chemical potential comes from Gibbs.
Dave, when did you first interact with Carl Sagan? And was he already famous at this point?
At that point, he had not yet appeared in the Johnny Carson show, which was the very well-known late evening TV program, The Tonight Show. And so Carl was known in a particular scientific community. He had been denied tenure at Harvard and came to Cornell, and he was known to be interested in the question of life and the universe, moderately well regarded as a scientist, but he became famous in the general public through Johnny Carson's enthusiasm for astronomy. And so when he first showed up in the Johnny Carson show, I saw it. I had to wait until 1 a.m. in the morning because he was the last person on the show and there wasn't much time left. In those days, the Tonight Show went until 1 a.m. Eastern time. And finally, Carl was there, and he has a very good presence, which works well with the general public. And Johnny loved him and brought him back. And of course, he could subsequently talk about the Viking mission, which he was involved in, which went to Mars. And he had a colorful way of talking about the nature of the universe and life and space and so forth. And many years later, of course, there was the Cosmos TV show, which was actually done in Los Angeles. So he became much better known still. But I did have a lot of interaction with him in later years, as well as at Cornell. But at Cornell, it was just taking a class from him. And he was responsible for the first thing I did, which led to a completed piece of work in planetary science, because in his class, he said a term project, and I wrote up a discussion of planetary magnetic fields, which included some new stuff. And he liked it, and he said, well, you should publish it. And so I wrote it up for the journal for which he was editor, which is Icarus. And so I already got to know him as a student.
So I'm looking for that dramatic narrative turn where you commit intellectually, academically to planetary science. Is it Carl Sagan's influence? Is that part of the story?
It's part of the story, but I think it's mainly Ed Salpeter and the fact that he was temporarily interested in giant planets.
Who else was on your thesis committee?
I don't remember all of the membership, and the committee changed. There was a committee that decided whether I should continue to do a thesis, and that's a qualifying exam. And at that point, you don't have a thesis. And that certainly had Hans Bethe and Ed Salpeter and Neil Ashcroft, and there must have been one other person whose name I don't remember. In the final exam, it would have been Ed Salpeter, Neil Ashcroft, probably Bob Silsby or somebody like that I think somebody who did infrared work. So it would have been a solid state physicist, but no, I don't remember.
How did you get involved in the complex work that was run by the National Research Council?
Jerry Wasserberg, who was, of course, a professor at Caltech and very well known in geochemistry, was chair of that committee, and he was looking for expertise in the area of giant planets. And he asked Ed Salpeter, and Ed said, no, I don't want to do it, which is very typical of Ed, although he did work on Jason. It's a rather special committee. So Ed said, no, I don't want to do it. Why don't you try my student? So something very unusual happened, because normally that committee would be people who already have established their careers or are well into their careers. This is the early days of planetary science. This is perhaps 1974 or thereabouts. And so I'm sitting in my office at Cornell in Clark Hall, and I get a call from this guy I know nothing about, called Jerry Wasserberg, and he persuades me to be on the committee. It wasn't that hard for him to persuade me. It sounded very intriguing. And it was a kind of important committee. It was an interesting and eye-opening experience that required traveling to Washington, D.C. and to Seattle, maybe elsewhere. Of course, eventually I had to quit the committee because I left the United States. But I did get involved in discussions that concerned the future of planetary exploration in a fairly major way. At that point, there was a controversy or a conflict between the Jet Propulsion Lab and NASA Ames, which had to do with the kind of spacecraft that you might send on a future mission to Jupiter, the mission that eventually became Galileo. These things happen over a long period of time, so discussions about these things were already taking place in the mid-70s. And the difference was that JPL was putting forward missions that were three-axis stabilized spacecraft that were good for imaging, not so good for magnetic fields. They already had expertise in that area. Of course, some company was building the spacecraft, but it's a question of instrumentation and so forth. NASA Ames was more in the pioneer mode, which are spinning spacecraft, and there was advocacy for what you would call a magnetospheric mission. On that committee that Jerry Wasserberg chaired was Jim Van Allen, who I got to know. In fact, we had a meeting right here at Caltech, in this building even, that I'm sitting in right now, in the mid-70s, when I was still a student. Jim Van Allen wanted a mission that went way out from Jupiter, measured the magnetic field. I mean, magnetospheres have all sorts of wonderful phenomena, and so you can imagine people advocating a mission of that kind. And this was in the context of a period where, for many people, the Galilean satellites were not interesting. Nowadays, that sounds ridiculous because they're planets in their own right. They have all sorts of fascinating stuff. Io has volcanism. Ganymede has a crazy surface. Europa has an ocean underneath the ice, so on and so forth. And Callisto is the ugly stepsister who does its own thing. But back there, they were just fuzzy balls. And so it was not so obvious that you should devise a mission, as we eventually did, that got really good images of the satellites and stayed close into Jupiter. So that was an important decision. We were also involved in discussions, as always happens with NASA, about the funding of a mission to Venus called Pioneer Venus, and whether or not that would get canceled and so on and so forth. So you can debate whether complex, which now has a different name, I'm still on it, which is ridiculous. Not all that time, but I'm on it for the third time. You can debate whether those committees have a lot of effect. There are some people who say, with cause, that it's a waste of time being on committees like this, because what happens is that you make reports and the reports get filed away. And NASA can say to Congress that we ask the opinion of scientists and so on and so forth. But there are occasions where it can be important, and I think that was actually an important time.
Who was driving the most important research mission that NASA wanted to do? What was your sense in the mid-1970s of those big decisions with regard to planetary science and research?
I'm not sure that there was a single person. Certainly there was interest in Mars, and Carl Sagan was involved in Viking. He was a prominent figure by that point. I don't know that you can, it could just be that I was too young to really know who were the power players. So I'm not sure that there's anyone in particular.
After you defended, what opportunities were available to you? And given your status, what were you trying to accomplish?
The world has changed enormously. Back then, the number of positions that could be called planetary science could be counted on a single hand. Very small in number. The field was young. There might have been a number of people who were hired in the late 60s, including at places like Caltech. But the number of departments that did anything that could be called planetary science was small. So the opportunities were small. I did not find that depressing, because somehow at that point, I just wasn't too worried. I enjoyed doing science. I wasn't focused that much on concerns about career path. But I had come to the United States with support from the Fulbright program, which is an international program that supports people within the US to go elsewhere, and importantly supports people outside the US to come to the United States. And one aspect of that program is travel support. I came to the United States with money provided by Fulbright, travel support, not a stipend, which was what Cornell gave me to be a teaching assistant initially and subsequently research. So I knew, although I did not really understand the legal aspects, which were murky, I knew that there was this expectation that I go back. But what did go back mean? If you're in the United States and looking at a map and you don't know much about geography anyway, Australia and New Zealand look more or less the same thing. So when a position was advertised in an area that did not look much like what I had done, geophysical fluid dynamics, at Australian National University in Canberra, Australia, I applied. It's the only application I made, and I got it. So I didn't think about it that much. I wasn't trying that hard to find a planetary science position in the United States at that particular point, because of this notion that you should go back. And so that's what I did. Although, of course, within 1 year of going to Australia, I was coming back to the United States, traveling around, trying to get people interested in me and finding a position, which I did at UCLA.
I'll ask the same question that I did at the outset of this conversation when you got to the United States. When you got to Australia, culturally, what were some of your experiences, and what might have been even disorienting given that New Zealand is close and yet still far?
Well, certainly Australia was much more like New Zealand, but again, somewhat different. In those days, more so than now, more cosmopolitan, more like the United States. I think the transition of living in Australia was actually in many ways easier because it was intermediate between what you see in the United States and what you see in New Zealand. So it was not really that difficult to figure out how to live in Australia. Of course, the physical environment is different. Australia, Canberra, that is very hot in the summer. It's actually quite cold in the winter. And there are interesting native species. So I had interesting close encounters with snakes, which was novel, and got to know the natural environment. Once saw a koala in the fork of a tree just driving down the road, and pulled over, and there was the koala happily munching away in the tree, totally unconcerned about its environment, things like that.
What was your home department at ANU?
So that was the Research School of Earth Sciences, and I think it was a matter of luck, serendipity, that I applied there because they had just hired a very distinguished geophysical fluid dynamicist, Stuart Turner, who had worked at Cambridge in England, had worked with G.I. Taylor, the lead person in the world in a particular kind of fluid dynamics, which has some application to planets. And so that was the connection.
Did you see this as an opportunity to expand on your thesis research or to take on new research areas?
I did take on new things. I got involved in thinking about how the Earth worked, how the Earth cooled off over time, a subject that is still unsolved, somewhat controversial at the time. Worked on aspects of plate tectonics. The Research School of Earth Sciences at that time had a tradition that is in many ways an English tradition of tea, morning tea and afternoon tea. And at that time, that meant meeting people in the morning, and out of that came some work that was collaborative about how big G, Newton's gravitational constant, might have varied across geological time, and I was able to provide some theoretical constraints for that on top of the paleomagnetic constraints at that time. The research school was a world leader in understanding paleomagnetic data. So there was a good combination, and I got to know a very distinguished and very distinctive scientist, Ted Ringwood, one of the world leaders in geochemistry. Got interested in the origin of the moon because he was interested in that. So it was a stimulating time, and it was an opportunity to do things that were completely unrelated from my thesis.
And another nomenclature question at ANU, geophysics, earth science, planetary science, how are these terms used there?
Well, certainly there wasn't planetary science as we know it now. There were people who were interested in the moon because they had been involved in the Apollo project. The Apollo program which was mostly in the United States, actually involved scientists in Australia and to some extent in Europe through the need to look in detail at the rocks. I mean, the Apollo program brought back a ton of rocks, a lot of which are still sitting there in Houston. And you could analyze them. The Research School of Earth Sciences had the ability to do sophisticated analysis. They still do. And so people were interested in the moon. They were a little bit interested in other planets. Ted Ringwood had some interest in Venus, for example. But mainly it was geophysics and earth science in particular. And so I got to learn about that subject.
What was Stu Turner working on at the time you connected with him?
He had started up some laboratory work at Australian National University. There was a student there, Ross Griffiths, who I got to know. The work was in many cases what we call double diffusive convection, which is a bit of a mouthful, but the essence of it, the common feature of all that work is the need to understand how fluids flow when there is something else in the liquid that changes the density. So if you have something dissolved like salt or sugar, remarkably, I had even done a bit of work like that as an undergraduate in New Zealand back in 1970. I did not get involved much in that, except, of course, that it has relevance to understanding planets and astonishingly has become perhaps even more important in understanding how Jupiter works, how exoplanets work. So there is a common feature there. The common feature is how to understand fluids where the density is affected by temperature, which is the obvious thing to think about, natural convection, but also how the fluid behaves if the density is affected by composition, and if you have both things present. If you have, for example, salty water that is cold and less salty water that is hot, these things have different densities. They can even have similar densities if it's hot salty water and cold fresh water. Do they mix? How do they convect? Questions like that.
Did you want to return to the United States because you wanted to pursue more work in planetary science? Was that simply not available in Australia?
Yes. The United States was the natural place to be if you wanted to do planetary science. I think in retrospect, you could have imagined doing some of the same things, staying in Australia, although you would have had to do it as an isolated scientist. There are people who do that successfully, especially in New Zealand, but also in Australia. Maybe in France. France has quite an active community and people doing planetary science. In those days, linked somewhat to the Soviet Union, which still existed, which still had a substantial program. Going to Russia was not an option. The United States had a strong program because of NASA, and that was attractive. I have to admit that for me, my interests were somewhat ivory tower, somewhat abstract. So I didn't actually feel as if I had to be associated with missions. I've come to appreciate the importance of missions and the attractiveness of being involved in actually doing measurements. But certainly being in the United States at one of the top institutions in the United States was attractive. That was the place to be.
Did you recognize at some point that your academic interest means that you would make a life for yourself in the United States, that you would not be going home to New Zealand?
I think that I realized that, although I didn't give it much thought. To me, science is so important to what I find interesting in life in general that that's what drove my decisions. And so I didn't feel a great deal of tension, even though New Zealand is an attractive place to live. It's a nice place to live. And of course, in later years, I got offers. I was offered the opportunity to be a professor of geophysics back in the school where I got my undergraduate degree in Wellington. I was offered a similar kind of position informally in Auckland, which is even bigger. But they're not attractive to me because I'm in the country where the most interesting science for me is being done.
Dave, tell me about your interactions with Freeman Dyson at the Institute.
So Freeman Dyson he's no longer alive, a fascinating character. And I knew of him because Ed knew him and because he had spent time at Cornell, although when I was at Cornell, of course, he was at the Institute for Advanced Studies. So Freeman knew about me through Ed, and maybe through my work on Jupiter, which had some relationship to things he had done. And when I visited the United States from Australia in 1977, I had lunch with him. It was a strange experience. I was at Princeton and I gave a seminar. And that's also where I met Rose Molokowski and his family. He had a house within walking distance. Princeton is nice that way. And so I was staying overnight in Princeton and had agreed to meet up with Freeman at the Institute for Advanced Studies, which I thought of as being just down the road. And so I set out to walk to the Institute of Advanced Studies, which of course is not difficult to do if you know the right direction. But I actually got lost. It was amusing. And eventually I found the Institute. I was somewhat flustered at that point. Freeman was pacing up and down in front. And so we met, and we went inside and we had lunch. And Freeman said to me, "Why don't you think about objects that are like Jupiter but more massive?" And of course, nowadays that would sound completely natural. But at that point, this was a novel idea. There was one other person who had worked on such objects and had even named them, and I met her later. That was Jill Carter, and she became director of the SETI Institute in the Bay Area.
Dave, what advances in observation would have made Freeman's advice feasible at all?
So that's the amusing part about it. At that point, there were no observations.
Yeah.
In fact, the observational story blew up a decade later and became brown dwarfs. And in the early days of brown dwarfs, we would all joke because what would happen is that somebody would make a huge splash and they would publish a paper saying, "I found a brown dwarf." And then a year later, they would say, "Oops, it wasn't a brown dwarf after all." But then finally, they actually survived test. And we still talk about the brown dwarf desert. There's a very interesting phenomenon that I still think is not fully understood, which is that when you go to really low mass objects and try to make them the way we make stars, that there aren't a lot of them. I'm talking about objects that lie in the mass range between the bottom of the main sequence where the number is already dropping off and things that might be called planets, which would be 10 times the mass of Jupiter. So just to set the scale, we have Jupiter had 10 times the mass of Jupiter, which is of significance because that's the onset of deuterium burning. It's much easier to have thermonuclear ignition with deuterium than with ordinary hydrogen. Then you have to go up to 70 Jupiter masses, and that's the bottom of what we call the main sequence, defined as objects that burn hydrogen, as does the sun. And then, of course, you just go up to much more massive objects. The sun, by the way, is, people think the sun is an ordinary star. Most stars are less massive than the sun. The sun is 1,000 times the mass of Jupiter. So anyway, brown dwarfs are bodies that are like Jupiter because they don't have much thermonuclear reaction, and so they cool to become degenerate bodies. Degenerate is a condensed matter physics word. It means that the support against gravity is provided by the Fermi pressure of the electrons.
As a gauge in the maturity of the field in planetary science, as you were going on the job market, were there positions available? Were there distinct planetary science departments that were hiring at this point?
I did not try very hard, so I'm not really sure, but I certainly had the impression that there were very few positions. And I think that was the nature of the times. The NASA funding had declined. The number of people going into the field was fairly small. If you went to a conference on planetary science, you could put everybody in one room. So it was very much a different time. And the science was different. It's funny to reflect on that. It's very much the case that even though the jobs were few in number, the opportunities in some sense were substantial because there weren't many people doing things. There wasn't a lot of competition even. So to compare it with what happens now, what I see now is a very large number of people wanting to do it. The number of positions has grown dramatically, but the number wanting to do it has grown even more. So you talk to a young person now, they feel under considerable stress, and they're in postdoc positions, and there are a lot of postdoc programs. So there's a lot of funding now. It's really quite remarkable. Before I was talking to you, I was on a Zoom conference with people involved in what is called 51PEG, which is a program for people who do exoplanets. And there's lots of people, and they get full funding for several years. And there are other programs. There's a Carl Sagan program. There's various other fellowships. So there are opportunities for people in excess of the positions available at universities or positions available at NASA centers. So it's much more competitive now. It's a more difficult field in some ways, a more mature, although there are abundant opportunities in observation because the explosion of information about exoplanets has revolutionized the subject. You now have lots of people looking at spectra, looking at various aspects of planets around other stars, all sorts of things that you couldn't even think of doing back in the early days of planetary science.
And what was available to you? Where did you end up going?
What was available to me was, at that time, from an observational point, a little bit of data from the Pioneer missions, which had gone past Jupiter and Saturn. And there was the beginning of what was really quite a major development, which did not happen, well, was starting to happen in the mid-70s, but didn't really fully blossom until the 80s, and that was Voyager. So Voyager was arguably the most successful planetary science exploration of all time until now, perhaps ever. Actually run by Ed Stone, who I knew, and who is a professor here at Caltech. And two spacecraft that visited Jupiter and Saturn. One of them visited also Uranus and Neptune. So that was an explosion of information about the planets in the outer part of our solar system. There is an interesting story that I have to relate related to the Voyager mission. The concept of the Voyager mission was originally something called the Grand Tour, and it was conceived by a Caltech student working at JPL in the 1960s, somebody I met only a year or so ago. His name was Gary Flandreau, and he figured out that the gravitational slingshot effect, which was already known, was known by the people who worked with the Nazi program, with Werner von Braun. They published on it. So that idea of going to the outer part of our solar system was already there as a theory in the 60s, and it was realized that the configuration of the planets could enable you to go Jupiter, Saturn, Uranus, Neptune, and even Pluto. And they didn't do Pluto. And the whole thing got delayed a bit. It was never really a grand tour. But the Voyager program grew out of that idea. So it's very much linked to Caltech. Of course, I didn't know these things until much more recently.
Tell me about the opportunity to join the faculty at UCLA.
So UCLA was advertising a position in honor of Bill Libby, who had worked in the Manhattan Project. That position was not in planetary science specifically. It was more broadly advertised, and it was not a tenure position. So it was a fixed term position, but otherwise had all the attributes of being an assistant professor. And I applied to that because, at least as far as I could tell, it was the only thing at that time that was attractive. This would have been 1978, perhaps, and I got it. I learned later from Leon Napoff about some of the competition for that, which included people who were doing earth science. So I ended up at UCLA in 1978 after spending 2 years at Research School of Earth Sciences in Canberra.
What department did you join at UCLA?
So that was the Department of Earth and Space Science. I had someone who took an interest in me. He had met me already at a famous Jupiter conference back in 1974 or 75. His name was Bill Cowler. He was a famous geodesist, no longer alive. And he was in what we would now call planetary science, although he also did things that could be labeled geophysics, certainly geodesy. He was one of the pioneers in geodesy, which is a central technique for understanding satellite orbits and understanding the gravity of planets.
Did you enjoy Southern California?
Yeah, so Southern California is different from upstate New York. And I got used to Southern California. The climate is nice. Rode my bike back and forth from an apartment I had on Bundy Drive, the same drive that O.J. Simpson made famous years later, a different part of Bundy Drive. Riding my bike through Westwood, through what was advertised in those days, it might still be true, as the most congested part of the United States. Traffic was enormous. I mean, along Veteran Boulevard and along Westwood, just enormous number of vehicles, 6-lane roads and so forth. So somewhat of a challenge to ride your bike, but UCLA was nice. And it was an interesting experience. And I even taught a basic class in earth science, even though I had never taken a basic class in earth science. So I stayed ahead of the students by reading an appropriate textbook by Preston Sieber. And of course, started on some important scientific projects.
Dave, now that you're in your first faculty position, I wonder in what ways you thought your own educational trajectory, which was in the physics department at Cornell, in what way did that background serve you well in these new fields of research? And in what ways were you perhaps playing catch up in ways that you might not otherwise would have had this been something that you pursued more centrally in graduate school?
Well, I didn't feel uncomfortable. It's interesting. I mean, my background is indeed physics, but I had some inclination towards the kind of science that is central to understanding how the Earth works. I had been interested in that already. It just seemed like a natural fix. It's true that you had to learn, and I did learn, some basic geology, nature of various rocks and so forth. But it was a comfortable enough transition, and I think it worked out fine.
A rather fun question. I'm not sure how concrete an answer you can provide, but when you have on your research agenda Saturn, Jupiter, Earth, Mars, in what ways do you treat Earth as just another planet in the solar system? And in what ways is it most obviously not that, because it's our home and it's close to us?
When I work on the Earth, I treat it as just another planet, and I think of it that way. The difference comes when you compare with data, and you can take advantage of the fact that there are aspects of the Earth that we know much better. And the most obvious difference is that we have seismology. Of course, we are starting to get seismology in other planets, but in the case of the Earth, we had a great deal of information about the density distribution, about the existence of a rather sharp interface between the core and the mantle, about the behavior of water and so forth. Things that you simply did not have for other planets. But a lot of the basic questions, at least at that time, perhaps still, are not answered, like exactly what goes on with Earth's magnetic field. How has it behaved through time? How does plate tectonics work through time? How does the heat flow change with time? These are sort of the kinds of questions that can be asked for the Earth and for other planets, and you tend to approach them with a common point of view.
Beyond the biosphere, once you get below the ground, how unique is the Earth in the solar system?
So say the question again, how?
Beyond, obviously, the biosphere, beyond the obvious fact that Earth supports life, below that, below the surface, what do we know about how unique or not the Earth is relative to other planets?
It's an interesting question. I don't think we know the answer for certain. The suspicion would be that the existence of life on Earth does not have a profound effect on the nature of the Earth at depth. But the truth is, we don't really know. When I say at depth, I mean, of course, much deeper than 10 kilometers. We have reasons to think that there are organisms that live beneath Earth's surface, but conditions become pretty difficult for life once you get deeper than about 10 kilometers. There may be some consequences for the recycling of material, for the isotopic makeup of the Earth. Certainly people who are interested in the history of life on Earth look at the isotopic makeup of material on Earth, and some of that gets recycled. So there may be consequences for the relative abundance of carbon isotopes, for example, which are affected. There's no doubt that the biosphere, that the existence of life on Earth has had a profound consequence for the nature of Earth's atmosphere and for the nature of the ocean, although somewhat less so. And for the nature of the sediments that we have, there are a lot of sediments on Earth that have been affected by biological activity. So in that sense, the superficial Earth is profoundly affected by biology. In fact, you could argue that in a certain sense, the existence of life on Earth is relatively easy to find. It's not clear that that's true for Mars or any other planet.
Is it then, in your view, too great a leap of logic to deduce that if the Earth is unique in its ability to support life, by definition, wouldn't that mean that its deep interior must be different than other planets? Or are those perhaps unconnected?
I think it's unconnected. I don't see a major link. Why? Because as I see it, life as we know it, which exists at fairly low pressure and makes use of water in its liquid phase, is a property of the surface environment. And that environment is not much affected by what goes on inside the planet. It is somewhat affected. Volcanism matters. Plate tectonics matters. But those are still superficial aspects of how the planet behaves. And they may even have some commonality. You are asking a very interesting and perhaps profound question. And I have thought about this, but I'm hesitating with my answer because I don't think there is one, at least not one that I'm comfortable with. It has been suggested, I've even suggested it myself, that plate tectonics is an important part of life. Plate tectonics produces variation. You might argue that life, or at least the particular way that it developed on Earth, is affected by the presence of change. If you had a planet that was boring, meaning that it had a very constant yet suitable environment for life, then maybe life would behave differently. I mean, if everywhere was like Southern California, that might not be good. I don't know. I mean, that's just speculation because we don't know. I do, by the way, have rather strong opinions about notions of habitability. I think that people make too much fuss about this. I think that the notion that the Earth is somehow particularly well suited is an extremely anthropocentric point of view. I don't see why we necessarily should exclude life in the clouds of Jupiter. And by the way, there's been a book written about this, and there was a paper that Carl Sagan asked me to review when I was a student at Cornell on exactly that subject. There's a paper written by Carl Sagan and Ed Salpeter. It's a very scholarly paper about life in the atmosphere of Jupiter. A lot of people don't know about this. I don't see anything wrong with that. There's plenty of water in the atmosphere of Jupiter. It's pleasant if you choose the right level. Of course, you might get carried by convection to nasty places, either up or down. So it's not obvious that this would work. But I think there's a problem if you're really hot. It's not clear to me that there's a problem on Pluto, because inside Pluto you have oceans, you have energy sources, not as much as sunlight, but the bottom line is I don't think the Earth is that special. But of course, once you get into this game of talking about life, you're talking about things that are highly speculative, and we're just going to have to wait for discoveries.
Well, while we're in that neighborhood of pure speculation, what has your research suggested about the possibility that life formed on Earth from alien sources? In other words, from microbes or bacteria, from asteroid impacts and things like that?
I think it's a possibility. I have a colleague, Joe Kirschvink, who thinks that we came from Mars. I argued this once with Sam Epstein, who was a very distinguished geochemist here at Caltech did some of the pioneering work on carbon and oxygen isotopes and many other things. And my argument with Sam had to do with the idea of a magic bullet. My definition of a magic bullet is something that comes from space that is the seed for life. This is a metaphor, of course. But what I said to him, and what I would still say, is that when I think about the early Earth, I think about all sorts of possibilities happening. And when I think about stuff from space, I think that a lot of it gets vaporized upon arrival and not suitable. Obviously, if I send in a meteorite, we know what happens to a meteorite. A meteorite survives through the Earth's atmosphere. Organisms can survive within meteorites, but meteorites are not typical delivery to the Earth. And why should you bother anyway? Because that's just a small fraction of the stuff delivered. So I see a richness, a diversity of environments and process in the early Earth that could lead to the things that might be necessary to make structure. And I don't see the need to invoke something from space. That, of course, is not an argument about exclusion. It's just an argument that perhaps life could start on Earth of its own accord.
Back to the world of observation and away from speculation, what were some of the advances when you were at UCLA to study Saturn and its magnetic field?
So we already had some data, and I suppose it must have been pioneered. I actually don't remember the details. It certainly wasn't radioastronomical, although Saturn's magnetic field was actually detected from Earth orbit before we went there. It was an IN-6 spacecraft, but that would not have given the dipole tilt. So certainly one of the most important things that I did scientifically was at UCLA, began certainly at UCLA and was mostly at UCLA. And that was the thought that you could explain why Saturn had a magnetic field that was almost aligned with the spin axis, did not have a dipole tilt, and therefore was different from Jupiter, different from the Earth, certainly different from the Sun. And that was because of a fundamental physical effect that you could create in the lab, in which if you placed yourself in a frame of reference where you saw the field as time varying and you had a conductor, then through the electromagnetic skin effect, you could attenuate that field. This is a well-known consequence of Faraday's laws. And so I must have already started thinking about that at UCLA. It was completed at Caltech. I remember giving a seminar at Caltech, but that was certainly something that I did at that time that was different from worrying about whether helium could form rain.
Dave, tell me about your interactions with Jerry Schubert and your work on thermal history of terrestrial planets.
So that was certainly something that was primarily linked to my 2 years at UCLA. I don't remember the specifics of how it began. I do know that it was not entirely Jerry Schubert. It was partly me because I was already interested in thermal history. Already when I was in Canberra in Australia, I had tried to understand how the Earth cooled through geologic time, and so I had already been thinking about how convection works in a solid. But Jerry was interested in the same kind of thing, and so the project developed in which we coupled the behavior of the core of the planet to the convection in the overlying mantle. And exactly how those ideas developed is no longer clear to me, but it certainly led to the recognition that you might be able to build a story about the different magnetic fields observed for the terrestrial planets. This was work motivated by Mercury, Venus, Earth, and Mars, that you might understand their differences and similarities through thinking about the nature of their cores and the extent to which the core could cool because of the overlying convection in the mantle. And in developing that story, it became apparent to me that the Venus could be different from the Earth because Venus did not have an inner core. Earth does. And we know, or at least we think we know, that right now, a key aspect of understanding why the Earth continues to have a substantial magnetic field is the presence of the inner core. The inner core, as it grows and as it excludes light elements, providing a gravitational energy source together with latent heat, the inner core, as it grows, provides an energy source for Earth's magnetic field. There are other ways of explaining Venus, none of which involve its rotation rate. People will always mention the fact that Venus rotates slowly. I don't think that's relevant. If anything, slow rotation is good for a dynamo. But Earth's, the difference between Earth and Venus having to do with the slight difference in mass, slight difference in temperature, different convective regime, which is a later idea, actually. These things were beginning to be part of my thinking about how these planets behave. Jerry Schubert was crucial. He was important in encouraging this, and he also played a central role in something that I'm bad at, which is that sometimes I do science and then can't be bothered writing it up. And so I can remember that at the time I left, or around about the time I left UCLA to come to Caltech, he was encouraging me to write it up. And basically, what ended up happening is that somebody else wrote it up. And that was Tillman's Pond.
You were scooped.
Tillman was a postdoc with Jerry Schubert, but he became an independent. He's a quite accomplished and well-known scientist. For many years, he was in Berlin. He came, of course, from Germany. He is now, or at least recently, was the director of the Institute for Space something or other in Bern, in Switzerland. So anyway, he's quite well known in the field.
Dave, you mentioned earlier that there was some controversy surrounding research on the Earth's core. What were those disagreements, and where did you fall in those discussions?
I think that it's not clear anymore what was really at the heart of the controversy. Certainly when I was in Australia, I can remember writing a paper about cooling of the Earth and sending it to Nature and having it rejected. First time I'd ever been rejected by Nature, one of the only times ever. And it was probably Dan McKenzie who was responsible for the rejection. Dan McKenzie, very famous scientist, who I met and got to know much better later on. I think part of it, but there were other people. There were people like Dick Peltier in Canada and other very distinguished scientists. Here's what I think was happening. What I think was happening is something that usually did not happen to me, which is that several people were thinking about the same problem at the same time. And that's a recipe for controversy. If you have several people who think that they know how something works and they have slightly different ideas, and they're working on it at the same time, and they get what are, in retrospect, not hugely different conclusions, they will still argue. This is this is a property of academia, probably of other aspects of life as well, that people will squabble over what are actually minor issues in the interests of establishing some kind of supremacy. It's like animals, right?
Henry Kissinger had a famous phrase along those lines. Dave, you mentioned gravity as it relates to the Earth's core. And again, this is a very abstract question, but given some of the central mysteries surrounding gravity and cosmology and our inability to understand why it's so weak and how we can't connect it with the other forces, is there a planetary science perspective that might enhance our broader understanding of gravity?
I doubt it. Most of what we do in planetary science in respect of gravity is, of course, Newtonian. There are corrections that we take care of that are general relativity. There are issues still that I think are unimportant that have to do with dark matter. So there are some people who would like to have us believe that dark matter, which may be elementary particles for all we know, interact very weakly, but could get captured in planets, so that you could imagine the particles, whatever they are, weakly interacting massive particles, say WIMPs, getting captured within the core of the Earth and then annihilating with each other and producing an energy source. So people have written things like that. That's not really connecting with the theory of gravity. I'm aware, of course, that there are people who want to think of gravity as an emergent property, as something like entropy. But I'm actually rather pragmatic when it comes to physics.
And can you explain, Dave, I'm sorry, when you say emergent property, what does that mean?
It means that the nature of gravity could emerge from purely geometric considerations. Of course, this is a different language from just writing down a Lagrangian or something in basic physics. But I'm just saying that in passing. I think, to finish what I was about to say, that to me, gravity is, and it's not, it doesn't have to be the role of physics to explain at some more fundamental level what it is. It just is.
Dave, to set the stage for our next talk, which is a great place to pick up, by the time you got the offer from Caltech, were you on the tenure track at UCLA? Were you tenured at that point?
Yes. So they were sufficiently impressed by me that they tenured me. I'm not clear about the timing.
But the position initially was not tenure track.
Correct. So they must have persuaded the dean or something. I don't know the details. I do know they wanted to keep me. I had a trajectory that was a little bit like Peter Goldberger, who had also been at UCLA and then was grabbed by Caltech. And so some people thought that this was a similar thing a decade later. It was even suggested to me that they might give me tenure, which is different from being on tenure track. But to me, I mean, I just wasn't anxious about that. So Caltech was not offering tenure. I did not ask for it. I just thought Caltech was a better place, and it's true.
That's a great place to pick up for next time.